Hello everybody. In this video we're going to go over section 13.3, Shifting Equilibria, Le Châtelier's Principle. And basically what Le Châtelier's Principle is going to allow us to do is to bring together a lot of the different concepts we've learned already and kind of give us a framework for thinking about them in the context of equilibria. So what we're going to do is we're going to describe the ways in which equilibrium systems can be stressed, and then we're going to predict the response of a stressed equilibrium using Le Châtelier's principle. So we've learned that equilibrium is a dynamic balance where the forward and reverse rates are equal. Okay, what we haven't talked about is what happens if I already have a system that's at equilibrium and then I go and make a change to that. Okay, so when subject to a change in conditions that affects these reaction rates differently, okay, we're going to call that a stress. All right, so it's going to affect the forward and reverse rates in different ways so that they're no longer balanced. All right, this results in a disturbance to the equilibrium. The system will undergo a net reaction in the direction of the greater rate, a shift, that will reestablish the equilibrium. And that leads us to Le Châtelier's principle. If an equilibrium system is stressed, the system will experience a shift in response to that stress that reestablishes the equilibrium. Now let's talk about our different stressors. Reaction rates are affected primarily by concentration. We saw that with the reactions rate law, and temperature, which we saw with the Arrhenius equation. An equilibrium stressed by a change in concentration will shift to reestablish equilibrium without any change in the value of the equilibrium constant. So this is no different than when we had QC not equal to K and we saw that there was a shift. An equilibrium stressed by a temperature change still reestablishes a different composition, but the reason that it did that is because the K value changed for that reaction. These K values are specific to the temperature. If I change the temperature, I'm going to have a new K value, and a new equilibrium is going to need to be established. So we're going to kind of formalize what we were talking before about the effects of concentration. All right. So again, when it's at equilibrium, our forward rate is going to equal our reverse rate. If the system is stressed by adding a reactant or removing a product, the rate of the forward reaction exceeds the reverse. Okay. And the system will proceed from the reactants towards the products, right to left or left to right. If I remove reactants or add products to an equilibrium system, the result is an increased rate for the reverse reaction. Now our reverse reaction is greater than our forward reaction, and the reaction proceeds from the products towards the reactants from the right to the left. We saw before that we can rationalize all the same effects of concentration by considering the reaction quotient, right? When the concentration of a reactant or product in a system at equilibrium is changed, the reaction quotient will no longer equal the equilibrium constant, and the reaction will proceed in the forward or reverse direction until this equilibrium is reestablished. So our rate logic is the exact same as the reaction quotient logic that we established in our last section. They're consistent with one another. Let's talk a little bit about the effect of changing the volume on a gas phase reaction. Okay, there are two scenarios here. If the total molar amounts of reactants and products are equal, a change in volume does not shift the equilibrium. If the molar amount of reactants and products are different, a change in volume will shift the equilibrium in a direction that better accommodates the volume change. And I think this is best seen with some examples here. So let's start off by considering this equilibrium, okay? Here I have 1 mole of hydrogen gas and 1 mole of iodine gas, 2 moles of reactants altogether. They're going to produce 2 moles of HI. So the net change in molar amounts here is 0. I start off with 2 moles. I end up with 2 moles. So there's not going to be any change there. If I write out the QP expression here, this is what I get. All right. Now, let's imagine for a second that we decrease the volume by a factor of 3. I have this exact same reaction mixture. It's now being held in a container that is 1/3 the size of the original container. This means that the partial pressures are all going to be tripled, right? Because they're behaving ideally, we can see that if we decrease the volume by 3, we're going to have 3 times the pressure. Okay. In that case, I plug that in here. All right. I get 3 times 3 is 9. I get 3 squared, that's 9. And they cancel each other out. And I still wind up with the exact same QP expression that I started off with. Okay. There was no change in the reaction quotient in this case. It wouldn't have mattered no matter what this reaction stoichiometry was, even if it was really complex, okay? So long as there's no net change in the number of moles, it will always work out mathematically that these are going to cancel. Let's look at a new system here, okay, where that's not true. I start off with 2 moles of NO2. I produce 2 moles of NO and 1 mole of O2. So I start off with 2 moles of reactants, and I wind up with 3 moles of product. Okay, I have a balance, a net change in the number of moles in the gas phase. I write out my QP expression here, and I still imagine reducing the volume down to 1/3 of its original volume. That means that my pressure is 3 times higher, and I plug those values in. Okay. I get 3 squared is 9. I get this 3 here. I wind up with 27 over 9. And my net result is that my QP is now 3 times higher than it was before. Okay. I've now disturbed this equilibrium where QP is going to be greater than the KP for this equilibrium. Okay. And things have to shift around until a new equilibrium is reached. So the net takeaway here is that when you do not have a balance of the total number of moles of reactants and the total number of moles of products, and you change the volume, you're going to have to reestablish a new equilibrium, and a chemical reaction will take place. Okay, so let's talk about the effect of temperature. We've seen what concentration does to a chemical equilibrium. Let's see what the effect of temperature is going to be. So what we're going to do is we're going to start by considering the simplest reversible elementary reaction here. Okay? We've seen that if we have the elementary reaction, we can derive those rate laws directly from it. So I can write a rate law for the forward reaction here, and I can write a rate law for the reverse reaction going the other way. I know that when I'm at equilibrium, the rate of the reverse reaction is going to equal the rate of the forward reaction. I can substitute in those rate laws, and then I can rearrange that to get B over A, products over reactants, okay? And that is equal to Kc. All right, and we can also see why these would be a constant at this point at a specific temperature, because these rate constants here are specific to temperature. Okay, and it also makes us understand why they would be different when we change the temperature. Okay, we saw from the Arrhenius equation that these K values are going to change with temperature. So if I put a new temperature, I get different K values, and they're going to lead to a new equilibrium constant for the reaction. What would be useful is to not just know that Kc is going to change with temperature, but to be able to predict how it's going to change. And there's a pretty easy way to conceptualize that. And what we're basically going to do is we're going to consider the enthalpy change of the reaction. So if I have this reaction here, I can see that I have a positive enthalpy. That means that this is a endothermic reaction. All right, I have to add heat in order for it to happen. So for the purposes of Le Chatelier's principle, what we can do is think of heat as if it was one of the reactants, right? I need heat plus this to get to that product. When I think about heat as one of the reactants, I can then think about how the change in temperature is going to affect this reaction, okay? If I increase the temperature, I'm going to increase the availability of heat, okay? I'm going to drive this reaction towards the products, which means that my Kc value would be higher. If I decrease the temperature, I'm going to decrease the availability of heat. That's going to drive this reaction towards the left, meaning my Kc value is lower than it would have been. So finally, let's talk about the effect of a catalyst. All right. We saw that the catalyst lowers the activation energy required. Okay. What it's not going to do is change the position of these reactants or of these products. All right. So there will be no net change in the equilibrium constant when we use a catalyst. Catalysts only affect the speed of the reaction, okay, so the kinetics. They do not change where the equilibrium is, okay? We will not be able to change the concentrations at which equilibrium is established, all right? So there's no effect that a catalyst has on the equilibrium position. They are unrelated. Okay?